So in a prior video, I had shown using a graphing calculator that the limit as x approaches 0 of sine of x over x is equal to 1. And this is in spite of sine of x over x actually not being defined at x equal to 0. Nevertheless, as x gets really close to 0, sine of x over x gets really close to 1, approaching from both the left and the right. In this video, what we're going to do is use the squeeze theorem to actually prove that the limit as x approaches 0 of sine of x over x is 1. The first thing I want to draw your attention to here is this unit circle, or what's supposed to be a unit circle. I know it may not look like a circle, but it's supposed to be the unit circle here. And we have triangle, right triangle OPQ. Well, this is the x-axis, so this is the x-axis. And this is the y-axis. And O is the origin. So we have right triangle OPQ, with O being on the origin, P being on the unit circle, and Q is the perpendicular dropped from the units from point P to the x-axis, or PQ is the perpendicular dropped from point P, which lies on the unit circle, to Q, which lies on the x-axis. So we have right triangle OPQ. We have sector OPS. This is this little chunk of a pie here, and it has angle theta. And here we have right triangle. Draw a little box here to denote that this is a right triangle, but it's right triangle ORS. So S is the point where the x-axis cuts the unit circle, and a perpendicular is extended up to point R here, and its point R is where the segment from O to point P, if it's extended, meets this perpendicular to the this tangent to the unit circle perpendicular to the x-axis. So you have right triangle OPQ, sector OPS, and right triangle ORS. So I'm just going to abbreviate these. I'm going to abbreviate this one, just triangle subscript OPQ. There should be an O here. Abbreviate this triangle symbol subscript O, or no, this is a sector. Here, let me erase this. Abbreviate this SEC subscript OPS. And I'm going to abbreviate right triangle ORS, the triangle symbol subscript ORS. So we know that the area of triangle OPQ, it seems to be less than the area of triangle sector OPS, which is in turn less than the area of this bigger right triangle ORS. This should be an A of right triangle ORS. Well, the way I've drawn everything here, let's find out what the areas of these two triangles, this triangle OPQ, ORS is, as well as the area of sector OPS. Well, OQ is the base of triangle OPQ, and QP or PQ is the height of triangle OPQ. And we know OQ, which is this segment here, its length is cosine of theta. But PQ, which is this segment, which is the height, its length is sine of theta. So half base times height, the area of triangle OPQ, so I'm just going to write it underneath here, is 1/2 sine theta times cosine theta. This should be just a less than sign. So what's the area of, and that's less than the area of this sector OPS. What's the area of sector OPS? We know the area of a circle is pi r squared. R is 1 here, so that would be pi times 1 squared, because we're dealing with a unit circle, so pi, that's just pi, right? Pi times 1 is pi. But what chunk of the circle are we looking at? We're looking at a chunk that's going to be, its fraction is going to be theta over 2 pi. So this is going to be theta over 2 pi times the area of the circle. So that's going to be theta over 2 pi. The area of the circle is just pi, right? So these cancel, and this is just theta over 2. But what about the area of this large right triangle, ORS? Well, OS, what's the best way to do this? I'm just gonna, this length here is 1, right? Because S is on the unit circle. This is, I just extended a segment from the y-axis parallel to the x-axis to where a vertical line intersects point S here on the unit circle, and this is equal to the length of OS here, and OS is on, S is on the unit circle, so OS's length is just 1. But what's the length of RS? If OS is length 1, right? And we know if OR is the hypotenuse of triangle ORS, right triangle ORS, and this is theta. Well, what's tangent of theta? Tangent of theta, the way theta is drawn, is going to be RS over OS. Well, OS is just 1, right? This is RS over 1. So this means that RS, and these 3 dots here arranged like this just means therefore. So therefore RS is equal to tangent of theta. But tangent of theta is the same thing as sine theta over cosine theta. But then if RS is sine theta over cosine theta, what's the area of triangle ORS? Well, we know OS is 1, right? And that's the base. RS is the height. It's sine theta over cosine theta. But we multiply 1 by sine theta over cosine theta, but then multiply that result by 1/2. So we get 1/2 sine theta over cosine theta is the area of triangle ORS. So underneath that, underneath this, I'm just going to write 1/2 times sine theta over cosine of theta. So if we look at these areas again, you see the area of OPQ is sine theta times cosine theta times 1/2. It's 1/2 sine theta times cosine theta. The area of sector OPS is going to be this theta over 2 pi. That tells you what fraction of the circle we're dealing with, times the area of the circle. The area of the circle is pi times r squared. R is 1. Pi times 1 squared is pi. So pi times theta over 2 pi. The pi's cancel. We get theta over 2. And the area of ORS, well, we found that RS is tangent of theta. OS is just 1. Tangent of theta is sine theta over cosine theta. 1 times sine theta over cosine theta is sine theta over cosine theta times 1/2 is 1/2 sine theta over cosine theta. So this inequality here, 1/2 sine theta times cosine theta, is less than theta over 2 pi, or theta over 2, excuse me, theta over 2, which is in turn less than 1/2 sine theta over cosine theta. Each of these portions of the inequality contain 1/2. So we can multiply every portion of this inequality by 2. So this will just become sine theta times cosine theta. It's less than theta, which is in turn less than sine theta over cosine theta. Now, remember, we're trying to prove that the limit as x tends to 0 of sine of x over x is 1. So ultimately, we want to, when we're using the squeeze theorem, obviously now we're dealing with theta, so it's going to be the limit as theta tends to 0 of sine theta over cosine theta. And that's the same thing as the limit as x tends to 0 of sine x over cosine of x. We're just using theta instead of x. But we want to make this theta look like sine theta over theta. So how do we do that? We're gonna have to divide everything by sine of theta. So ultimately you have to turn this into theta over sine of theta by dividing everything by sine of theta. And then we're gonna have to take the reciprocal to turn that into sine theta over cosine of theta, and we'll have to take the reciprocal of everything. But notice the way I've drawn the diagram here. Theta is positive. But remember that theta can approach 0 from both the positive and the negative sides. If theta were negative, right, what would this triangle here, this triangle here, I'll redraw this diagram above first. So I've redrawn a quick and dirty version of the diagram we were just taking a look at. So when theta is greater than 0, right, we had this right triangle OPQ, the sector OPS, and right triangle ORS. So ORS and OPQ are right triangle. But what if theta is less than 0? Well, I've drawn the origin is going to be where the origin is. P will be actually here, and I've labeled it as P prime. So we'll have right triangle OP. Q is going to be where it already is, right? Because it's on the x-axis. And this triangle is kind of going to be extended out like so. And this is R prime. So this is where R was, where the new R would be if theta were negative. So I'll call this theta 1 and theta 2, where theta 2 is just equal to negative theta 1. So this is if theta is negative, then you're dealing with identical right triangles here, but just reflected over the x-axis, and a sector that's identical but reflected over the x-axis. So back to our original diagram, we said that the area of this triangle was 1/2 sine theta cosine theta. The area of this sector, OPS, is theta over 2. The area of this big right triangle, ORS, was 1/2 sine theta over cosine theta. That's if theta is positive. If theta is negative, well, it's basically going to be the absolute value, right? Because all these are cosine theta is a length here, sine theta is a length here. So when we're concerned with lengths, we're concerned with absolute values. So even if theta is negative, when we're computing the areas, if we take absolute value of everything, then we have valid expressions for the area. So these areas, if they're like absolute value of sine theta, or absolute value, I should say absolute value of this whole thing, because we're if we allow this, the original expressions were for theta being greater than 0, but if we allow theta to also be negative, then these areas are equal to the absolute values of these things. And if we multiply all the areas by 2, these are the inequalities we get here. So the absolute value of sine theta times cosine theta is less than the absolute value of theta, which is in turn less than the absolute value of sine theta over cosine theta. We still somehow want to turn this absolute value of theta into theta over sine theta, and then into sine theta over theta. We have this absolute value here. How do we deal with that? Well, I'm going to start with this inequality here, and then we're going to be doing some algebra. So this is the expression rewritten here. This is the compound inequality rewritten here. Well, we know that the absolute value of a product is equivalent to the product of the absolute value. So this absolute value of sine theta cosine theta is the same thing as the absolute value of sine theta times the absolute value of cosine of theta, and which is less than the absolute value of theta, which is in turn less than, well, this absolute value of sine theta over cosine theta. Again, the absolute value of a quotient, okay, is the quotient of absolute values. So let me erase this. Okay, so this is equivalent to the absolute value of sine theta over the absolute value of cosine theta. Okay, so we ultimately want to turn this into something that looks like sine theta over theta. But first, let's turn it into theta over sine theta. Let's divide everything by sine theta. So, or, well, we can't. We have to deal with the absolute value here. So let's say we divided everything by the absolute value of sine theta. This stuff here divided by the absolute value of sine theta is 1 over the absolute value of cosine theta. This expression here divided by the absolute value of sine theta is just the absolute value of cosine of theta. And now to get from, well, this here can be rewritten as, here I'm just going to use up this space here. So these are interchangeable here. The middle part, because this is the quotient of absolute values, that's the same thing as the absolute value of the quotient. So the absolute value of theta over sine theta, which is less than 1 over the absolute value of cosine theta, and it's greater than the absolute value of cosine of theta. Okay, so let's say we take the reciprocal of everything, right? So this becomes, the middle part becomes the absolute value of sine theta over theta. This bit on the right becomes the absolute value of cosine of theta. Here, 1 second. Yeah, this here becomes the absolute value of cosine of theta, and this bit on the left becomes 1 over the absolute value of cosine of theta. But what happens to the signs? Well, we're taking the reciprocal of two quantities that are taking the reciprocal of a bunch of positive quantities, right? So when we do that, here we have absolute value of cosine of theta is less than 1 over the absolute value of cosine of theta. These are both positive quantities. So when we take the reciprocal, this will become greater than this here. So we're going to have to flip these signs. Okay, but I want you to notice one thing here. When theta is approaching 0 from either the left or the right, so from either negative values of theta, so that would be somewhere here, right? This fourth quadrant, or that would be from the left, and from the right be positive values of theta, that would be in the first quadrant. Cosine of theta is positive in both quadrants, right? So if cosine of theta is positive, then the absolute value of cosine of theta is equal to cosine of theta, right? So this is the same thing as saying 1 over cosine of theta is greater than the absolute value of sine of theta over theta, which is in turn greater than, and this is just cosine of theta, because if cosine of theta is positive, the absolute value of a positive quantity is equal to itself. But then what about this sine of theta over theta piece here? What you'll notice is when theta is positive, sine is also positive, right? Sine's the y coordinate. When theta is negative, here sine is also negative. If we're restricting ourselves from negative pi over 2 to pi over 2, which is a reasonable assumption because we're looking close to theta equal to 0. So if theta is positive, if sine theta is positive when theta is positive, and sine theta is negative when theta is negative, then sine theta over theta in the first quadrant will be a positive over a positive, which will be a positive. In the fourth quadrant, you'll have a negative over a negative, which will also be a positive. So there's no situation close to theta equals 0 where sine theta over theta is a negative number. Sine theta over theta is always positive close to theta equals 0, regardless of whether theta is positive or negative. So sine theta, absolute value of sine theta over theta is just equal to sine theta over theta. We can drop this absolute value as well. So now we just have this inequality here. 1 over cosine of theta is greater than sine of theta over theta, which is in turn greater than cosine of theta. So now it looks like we are ready to employ the squeeze theorem. So let's look at this limit. Let's look at the limit of this function on the left here. The limit as theta approaches 0 of 1 over cosine of theta. Well, as theta gets close to 0, cosine of theta gets close to 1. 1 over 1 is just 1, right? And the limit as theta approaches 0 of cosine of theta, that's this function, this right function here. As theta gets close to 0, cosine of theta just gets close to 1 as well. So that limit's 1 as well. Since the limits of these two functions here, these are equal to 1, then the limit, then we can just say, putting an arrow, then the limit as sine theta, limit as theta approaches 0 of sine theta over theta is also equal to 1. And this is equivalent to saying, this is the same thing as the limit as x approaches 0 of sine of x over x, and x has just been exchanged for theta. So we have finally proven that this limit is 1.